Thank you very much. Let me see if I can. Guess I just see if I can work this. So glad you all could make it out in spite of the pandemic. This is jointly with Sergey Tarima, who is here with me. Control L. Control L. Okay. You see, it's been a long time since I've been out and about. I actually had my work in adaptive designs until I met Sergey was pretty exclusively based on adaptive treatment allocation strategies. And he was interested in early stopping rules, group sequential design type aspects. And so what I saw when we ended up in a session together is that we were getting similar kinds of results from both kinds of adaptations. So we have a recent paper in Metrica, which is called Most Powerful Test Sequences with Early Stopping Options. And we really had to go pretty dense in order to please the reviewers. The main takeaway from that paper was really not getting most powerful tests. It was the likelihood framework that's developed in that paper. And as an alternative, you'll see as we go along. But and then a subsequent application of this likelihood framework was when we were asked to discuss a paper by Nigel Stallard, and that is on biometrics, on the Biometrics Online now. And one very common approach to group sequential designs analysis is to combine p-values from different stages. And what we show is with a very simple likelihood model, we can get exactly the same results you get from the combining p-values approach, but you also can look at many more questions from a likelihood approach that you can't do from the combining p-value approach. So standard work in group sequential designs focuses on controlling your type 1 error under a null hypothesis. And basically for a large part, and I'll note some exceptions, for a large part, the theoretical justification for group sequential designs is all done under this hypothesis, the null hypothesis, and that you're controlling type 1 error. And of course you want to do that, but our thesis is you can do more. And the big hurdle when the theory was all being developed was really computational, because if you make assumptions like you can get with martingale theory and large deviation theory, then your computational burden, you end up with nice asymptotic normal results, and your computational burden is really reduced. But if you go back to also some early papers, to analyze things, and I'll be more specific in a minute, the computational burden was multiple integration. And that really was a stopper, 30 years ago, but now it's not a problem. So there is literally no reason to make the simplifying assumptions that have been made earlier. So what I want to show you is, or entice you to look at, is a unified likelihood approach. Also motivating me is that, when I'm on a data safety monitoring board or whatever, no sooner is the decision made to stop or to make a decision, then somebody wants to know what the effect size is. So they want to estimate. And again, it's nice to have a more complete analysis framework when you want to go do your estimates. So we can do more, and I will continue. So I'm going to start from just as simple a construct as we can manage. And that is, we'll start with, you have two independent random variables, x1 and x2. And then we'll just say, okay, you're going to only look at X2 if X1's less than 2.18. And we're gonna look at the probability structure that happens when you make this decision and its consequences. So if you only look at X1, you have a nice normal random variable. The likelihood is the log of the density that's there at the top, and it's going to be maximized when your theta, which is the mean, is equal to the random variable you observed, X1. Now, if you observe X1 and X2 independently, then you have a normal random variable, a bivariate normal random variable on R2. And I may seem like I'm being very picky, but what we're going to see is if you don't have these observations observed independently, you're no longer on R2. And if you're no longer on R2, you don't have a normal distribution, because the normal distribution is defined, from minus infinity to plus infinity on the whole range. So right from my making these statements, some of the problems with assuming everything's normal when you're finished start to emerge. And so at the bottom is the likelihood function, log likelihood function for the two independent random variables. And the MLE, as you know, is the average of the two observations. So now we're going to suppose that X2 is only observed if X1 is below a cutoff value, 2.18. And now, if X1 were to be bigger than 2.18, you don't just have a missing X2, it's impossible. It's out of your sample space. It's impossible. So this random variable, which is the pair X1, X2, is not observable. It's not an observable random variable. And we want a probability measure defined on with regard to our observable random variables. So at the bottom there is the sample space that is actually available to you. That is, you have X1 if you're over the cutoff value, and if you're under the cutoff value, you have X1 with that restriction and X2. So all of that just by itself tells you that the two together, when you're finished, are not bivariate normal. And this is a little sketch of the support region. On the left, you have we'll just read it X1 and X2, but they could be standardized normal random variables. On the right, you have the cumulative versions of those random variables where you've taken X1 plus X2 or C1 plus C2. And so if you stop at stage one, you have a region of observable random variables that's to the right. And the only thing really to notice here is that these regions are not nested. When one develops survival analysis, you can observe the whole right line, the whole line out to wherever you stop, or somebody gets censored in the middle, you observe a part of that line. You definitely have nested observations, but these observations are not nested, which is important for the martingale theory and the large sample deviation theory, which is used often to justify normality. So I don't know why I switched to T1 and T2 here. I think I defined them actually on a later slide, but just think of them as your summary statistics. Your two sufficient statistics will actually, so let's just look at X and D. So D is the stopping stage. It's going to be 1 if your X1 is greater than 2.18, and it'll be 2 if otherwise. So it's actually also, in this simple case, your random sample size. And the sufficient statistics are both the X variables, whichever you observed, and D, that is the decision to observe one or two. And when you write out the density, you see there's the two terms there with the indicator function where you stopped. So you factor the likelihood into the two pieces that are determined by the stopping stage. And when you just look at the likelihood, it is, as is well known, that you really just have whatever was the case for the stopping rule that you ended up with. And some people don't think any further than this. They say, well, it doesn't matter where you stopped, the likelihood is whatever you had. And that so far is true. But what we really have is no longer an exponential family. We have a curved exponential family. And this was recognized by Efron and by Liu and Hall a long time ago, but those papers seem to have been published and everybody forgot about it. So here they are. And so if we rewrite our statistics with these indicator functions in here, we end up with a W1 and a W2 that go into the expression of the curved exponential family. And they're sufficient for theta. So it's not like just X bar is sufficient for theta. You got two things there, so you got a bivariate random variable. And again, when you do the likelihood function, you have these are the same two pieces we saw on the other slide, but divided by what is separated by what is the stopping stage. And the MLE is going to depend on whether you stopped at stage 1 or stopped at stage 2. So far you could have gotten to this point with the likelihood without thinking about it really at all. But what changes is when you go to take expectations. That is, if you take the expected value of your random variable, or you look at the information matrix, the Fisher information matrix. So as soon as you take an expectation, you're taking an expectation over a density, and that density is, as I showed you, not a normal random variable. It's not on the whole real line in R2, or the whole real box, or however you say it in R2. So the density is different, so your moments are different. And also the fact that you stopped is informative. It's not, and so when you so there is a cost to adapting, because you actually, if you think of Fisher information as a measure of information, then it is reduced by your having an informative stopping stage. So if you have, so we think about the cumulative test statistics. And so we have this density of our cumulative test statistic, D being the random variable for stopping that can take on these little d values. And so you can write the overall density as a sum of the densities over all the possible places you might have stopped with the indicator function. So in the end, you still just have the one you looked at. But this was actually the way it was introduced by Armitage, McPherson, and Rowe in 1969. Well, they looked at the piece over here on the right that goes with the density that you stopped with. And their formulation is the basis for all of the calculations that are done in the various software packages to confirm that, in fact, you have controlled for your type 1 error. And at the time, Armitage, wrote out his paper, he recognized that he was dealing with this one little piece. So again, as far as hypothesis testing and controlling for type 1 error is concerned, everything works as advertised, more or less. So just to show you some pictures. So say you haven't started your study yet, you want to plan your clinical trial. Well, usually you use what? You use the density for doing that. And what we see is that if you're under the null hypothesis, the density actually looks like this. It's got this little blip on the right hand for the for if in fact you decided to stop at stage 1. So this is different from saying conditional on the fact that you kept going and going and going, and you're only looking at, you know, what happens in the evaluation that is typically done for power, et cetera, is you construct this multivariate normal distribution, and then you sort of peel off the edges that weren't actually possible. And what we're talking about is building that construct up from the bottom, just clearly at the beginning. So here is the density of your your sufficient statistic, your summary statistic, your theta hat, your MLE, under the null hypothesis. But you're over here, if you're over here at the critical value that you actually use, then you see it's really quite non-normal looking. So, I mean, I haven't really clearly thought out the implications for this for design, but if you're thinking about wanting to do something more than just control for type 1 error, it seems to me that one should be thinking about what these densities really look like, and the fact that you might well stop at stage 1 and want to estimate your treatment effect. So let's look at that. Here's what happens if you stop at stage 1. You only observe stage 1. Again, on the left, we have the null hypothesis, theta equals 0. And on the right, we have the value of theta at the point, at the critical point for stopping. So again, I think this requires some discussion and some thought. That is, you know, you stopped for futility, or you stopped for toxicity, or for some reason you stopped the study early, and then you finish and you want to estimate your effect size. I mean, this is your density, not that normal density that you started with. Or maybe somebody can argue me otherwise. I don't know. I put at the bottom, I think that there should be some discussion, because lots of studies stop early, and everybody wants to know what the effect size was. So if you're calculating with respect to this density, it's quite different from calculating it with respect to the normal you started out with. Here's the density when you actually complete both stages. And this one on the left is why people feel so comfortable doing everything they do. It's the one that's based on you're under the null hypothesis, and B, you continued, you finished it as you planned. And it's actually not quite normal, but if anybody that does practical statistic would say, well, that's not bad, we don't care. But now you go over here and you get to you get your theta to actually be the critical value. And again, maybe it's not terrible, but you can see you can see a skewness. And if your theta were actually bigger than this, then the fact that this is really a mixture of two distributions gets the non-normality gets stronger and stronger. So it depends on what theta is. Some then sort of trying to put this together. One of the points is that the likelihood theory, if you can say it applies whether you had the fact that you had this curved exponential family. I mean, you can write that down. You didn't have to start with normal random variables. They could be bivariate, or they could be whatever. And we didn't use to sort of make the points we made here. We didn't use any asymptotics. And if you do use asymptotics, what we show in our papers is you're talking about 2 or 3 or interim stopping times, you can just use regular central limit theorems, and you don't get normality, you get mixtures, but you didn't have to invoke any large, fancy, any really complicated, fancy theory to do it. So again, the 2 papers I mentioned earlier, and the point was to show how to do things with the likelihood. And this just reviews the early effort in group sequential design to develop theory. Again, trying to spin off what they learned from survival analysis. And what we're proposing is that you go back and take a fresh look now that we're not as limited. So the repercussions of stopping is your support's not nested. You don't have bivariate random variables. Everything's calculable. It's not complicated. Your observable random variables, you've got 2 of them for 2 stages. You know, you got your stopping time and your regular statistic. And this is not computationally difficult to deal with. At least it's not for Sergey. So I'm going to close there and see if there's any questions.
I think we can leave all the questions at the end.
Okay.
How did it go?
Okay.